typically define our outcomes with capital letters. So, for example, heads. We might define the outcome as heads, tails. Okay? So, as I'm driving up to the stoplight, it could be heads, or my events might be S and G for stop versus go. Okay? All right. Now, the probability of any given event or given outcome is the number of ways the outcome can happen over the number of ways the event can happen. You guys, the outcome was a 1, the event was rolling a dice, yes? And I said, what's the probability you roll a 1? And you guys said 1 out of 6. Why? Because there's only one way the outcome of a 1 could happen. There are 6 different ways the event of rolling a dice could happen. What if I had asked you instead, what's the probability of odd? You would say, how many odd numbers are there on a dice? 3, right? So it would be 3 out of 6. This is okay. So when we do this, this is a fancy way of saying the probability formula you already know. Okay? All right. You guys, what is the probability when you roll a dice that it is not a 1? We said, by the way, the probability of a 1 was 1 out of 6, yeah? How'd you get that?
It's one side of the dice that you still have all the other numbers.
So you took the remaining, right? Okay, so 5 out of 6. 5 out of 6. Hey, you guys, what if I said the probability that Mr. Richards annoys me today is 60%? Ever good? He will. I'm going to have to shut my door at least 5 times this afternoon. It doesn't really happen with you guys that often because he doesn't teach a class second period, but I promise you, I spend a lot of time going, shh. Okay? You guys, what's the probability he doesn't annoy?
40%.
How'd you get that?
Well, everything's out of 100, but then you take the 60 and you subtract it.
Okay, so these 2 events are what we call complements. So a complement to an event is its exact opposite. Okay? And you can always do it. So the probability, and so we have a little notation. So if the probability of A, and so this, and then we might say AC, and that C stands for complement. Okay? The probability of AC is always going to be 1 minus the probability of A. Now, or you could say 100% minus the probability of A. I am not going to care if you write your probabilities as percents or decimals. Okay? So, I could easily call this 0.6. Yes? And then instead of saying 40%, you would say 1 minus 0.6 instead of 100% minus 60%. Same thing, okay? I don't care whatsoever about whether or not you write them as percents or decimals, okay? I'd like you to take probabilities to 3 decimal places, okay? And it wouldn't be like thinking long term of where we go after the probability unit, okay? It's not necessarily a terrible idea for you guys to start thinking about things as decimals instead of percentages in terms of foundationally for the next unit. However, I do recognize that for just about all of your academic career, you've been taught about percents as or like probability as a percent. So I'm not going to get picky about it. Does that make sense? I'll accept either answer. What I won't be okay with is calling this 0.6%. It's either 0.6 or it's 60%. But you can't just, once you calculate a probability, I don't want you to just throw a percent on the end. You have to actually turn that into a percent. Is this fair? Okay. All right. Another rule. All probabilities have to be somewhere between 0 and 1. You cannot say that something has a 110% chance of happening. Is everybody good? And if I take all the outcomes of a possible event, the sum of all of those will always be 1 or 100%. All right. So, some examples. Let's list the sample space of flipping 3 coins. And when we do the sample space, we kind of think through all the possible ways that could happen. So we are going to think about this almost as a first coin, second coin, third coin, because it's going to help us with probability, okay? All right, so what's my first possible outcome? Heads, heads, heads. What else? Oh, we have that one.
Is that all?
Heads, tails, heads.
Real quick, let's talk about how many there are going to be. You guys, how many possibilities are there for the first coin? 2. And then you're going to say, all right, after the first coin's heads, it has 2 new possibilities. And then 2 new possibilities. So 2 times 2 times 2. So how many total outcomes are there? 8. Yeah. So we are 3/4 of the way there. So we have heads, tails, tails. You guys, you know what I'm going to do? Sometimes, because this is like, I don't like doing this. Like, how do I know? Do I get them all? You want to map it out real quick? Remember when we talked about tree diagrams last semester? They are a tool to help us get to a sample space quickly. So let's see. What I'm going to do is kind of highlight as we do each one. So heads, heads, heads would be this one. Tails, tails, tails would be this one. Heads, tails, tails would be that one. Heads, heads, tails is that one. Tails, heads, heads is that one. And then tails, heads, tails. So what are we missing?
Heads, tails, heads.
Heads, tails, heads. And then tails, tails, heads. So do you have to do this? No. But man, would it be really easy to accidentally forget one of these? Right? Like to me, this is, and honestly, if I asked you to list the sample space and you gave me this tree diagram, I'd probably accept the tree diagram as your sample space, because that, like, to me, that's a very clearly communicated path of what all the possible outcomes are. Okay? Are we good? Okay, great. So, what is the probability of getting exactly one coin to come up heads? All right, so we go up here. That's how many ways can one heads happen over how many ways can flipping 3 coins happen. So what's my bottom number? How many ways can we flip these 3 coins? 8. Of those 8, how many had exactly 1 coin come up heads? Not that one, not that one, not that one. You guys seen how I did that?
Exactly or at least one?
Exactly 1.
Couldn't you just do, since you have 3 coins, they're all like 50%, so then you have 3 coins, they each have heads, so I just did 3.
So
Oh wait, where was I getting?
yes, okay, so can I push a little?
Yeah.
Okay. What if it was 4 and I said 2? You with me?
Yeah.
Okay. So, Teo, I love the way you're thinking, right? Because that's great. I promise. And if that were the test and you did that, I would figure it out. Like, that we could make some sense out of that. That's fine. Absolutely. It's going to get worse.
Yeah.
It's going to get to ones where, and then here's another question. Okay? So what if, instead of it being heads and tails and a coin, what if it was like 3 days in a row is Mr. Richards going to annoy me, and so now my probabilities are 60-40, and they're not all equally likely.
Yeah.
We will get to that at the end of next week.
Okay.
Everybody good? So, probability is complicated, right? Your strategy works if we keep it to like finding the probability of exactly 1.
Yeah.
Okay? The minute you get it away from exactly 1, that gets a little bit more messy.
Okay.
I love that Grace asked, are you guys good if I call this 3 8s and we're good with that one? Because there are 3 of the 8. But then Grace said, are you exactly 1 or at least 1?
I'm just counting the X's. I don't know why. I was looking at the X's. I said 3. I don't know why I said that, but
What? But you said at some point at least 1, yeah?
yeah.
What's the probability of getting at least 1 heads? Let's roll with this. Well, first of all, I'm going to write that a little differently. That my number of heads is greater than or equal to 1, yeah? Let's get these X's and stuff out. So that we can redo this, yeah? Yes or no?
Yeah.
Yes?
No.
Yes?
Yeah.
Cool? 7 8s? Okay, you guys. Are you ready for what is one of the hardest questions for kids? And they get like the problem of at least 1 is like this crazy hard concept, right? Are you guys with me that at least 1 is the exact opposite of none?
You lost me.
Okay. This was the only one that did not have a heads, yes?
Yes.
Is everybody with me? Which one is this one? How many heads does this one have? 0. So, greater than or equal to 1 in a probability event is the complement to 0. Is everybody good? So we could have said, instead of saying what is the probability of getting at least 1 heads, we could have said, well, what's the probability of getting 0 heads? And subtract from 1. Everybody okay? Okay. Lovely. All right, so we're just going to do the top of this page and we're going to be done, okay? Okay, ways we find probability. If I flipped 15 coins right now, and they all came up tails, would you guys be shocked?
Yes.
Why?
Because that's really, like, yeah,
It's really low?
probable.
It's pretty improbable, yeah. Did you calculate a probability to come up with that answer? No, you're basing it on your intuition, yeah. Subjective, intuitive, you guys, you do this based on feeling, based on your intuition. Now, that being said, this is my least favorite way to find a probability. Okay? Because human beings, all of us, are inherently flawed when it comes to understanding the chance of something can happen. Because we view our own experiences as the collective experiences. In reality, our experiences are all really different. You guys with me? Let me count. 1, 2, 3, 4, 5. I have 5 stoplights on the way home. I think that's right. I think I counted them all. Let's see. Grandview Avenue. And then after Grandview, the next one's where at Giant Eagle.
No, there's one, I like where that weird intersection is.
Oh, Northwest.
Yeah, Northwest.
My least favorite intersection of all time. Okay. That's weird because you have side streets that are not part of the intersection, right? You guys know what I'm talking about? Like, right, oh, I hate that. I hate that intersection. Then Giant Eagle. Then Olentangy. And then I know there's one. I think it's 7. That's 6. That's 6 stoplights. I have 6 stoplights. There's the one. I don't know how well you guys know the other side of Olentangy, but that's essentially how I go home. Okay, so 6 stoplights. I know typically I make 3 of them or 4 of them. Yeah? But driving down a different street, that's my experience is, okay, so maybe I hit a green light half the time. Or I can go through the stoplight half the time. But that's only based on that stretch of street and then based on my drives home at a very specific time of day, really. Or a drive in at a very specific time of day. Are you catching my drift, right? So that is my one experience, when in reality, okay, so if I approach a stoplight, that one experience is not a great... Do you guys see what I'm saying? When intuition is, not great. It's not a great way of calculating probability. Okay. So what I could do, and this helps inform intuitive, is instead of just, going on feeling, what I could do is every single day I could keep track of whether or not I go through that stoplight or not. Okay? So empirical or relative frequency, probability, this is a legitimate form to find probability, is do the event a large number of times. And see how often an outcome occurs. I have a couple of dice that I had Mr. Ginnert 3D print for me to be loaded. Right? I had him weight the dice for me just to see. But he didn't tell me which was which. So if I wanted to find the probability of a 1, a 2, a 3, a 4, a 5 on that dice, I know it's not a fair dice. He printed it so that it wouldn't be, right? So part of it was more dense than the other. Are you guys with me? So if I wanted to figure out the probability for each possible outcome, I could roll it and roll it and roll it and roll it. Just keep rolling this dice, right? And let's say I roll it 1,000 times, then I could say how often out of the 1,000 times did it come up 1? How often did it come up 2? That'd be a good guess at those probabilities. Is everybody good? And the more times I roll it, the better my guess would be. Yeah? Okay. Classical theoretical probability. this is the one we kind of talked about at the previous page. This is your overall understanding of probability. It is the number of ways for an outcome over the number of ways of an event. It's the classic desired over total. Three ways you could get exactly one heads over 8 possible ways you could roll the 3 dice. And by roll 3 dice, I mean flip 3 coins. Okay, last part. Huge idea. Okay. The law of large numbers says the more trials of an event, the closer the empirical probability matches the theoretical probability. If I do something for a large number of times, okay, if I roll a dice 12 times, right, I'm not going to get 2 1s, 2 2s, 2 3s, 2 4s, 2 5s, yeah? But if I roll a dice 600 times, I'll get about 100 of each. Okay? So short run, small number of trials, my empirical probabilities are bad. Okay, for a small number of trials, empirical probabilities are stupid. There's no point. Okay? You need a large number of trials for empirical probabilities to be useful. That's essentially what the law of large numbers says. We will talk about this in more detail next week for sure. Okay. All right. So tomorrow in class, you can work on the Excel lab. You won't